Dear students, how are you? I hope you are fine. I am also fine. Dear students, welcome to everybody in our Amadir Pathshala, conducted by Manipur Uccha Vidyalaya and College. Dear students, today I am going to start the lecture 3 on thermodynamics, chapter 1 of physics second paper, class 11 and 12. Dear students, learning outcomes. After studying this lesson, the students will be able to deduce an expression of work done for ideal gas in isothermal process. Also deduce an expression of work done for ideal gas in adiabatic process and solve some mathematical problem and creative questions. Now, first we will discuss work done for ideal gas in isothermal process. Dear students, you can see two figures, figure 1 and figure 2. In figure 1 is a cylinder. 1 mole of ideal gas is kept into the cylinder with frictionless piston. The volume, temperature and internal energy of the gas is T, V and U. The students, if a heat source is attached with the cylinder, then the heat transforms into the gas. As a result, the gas will increase and volume will also increase. Let the area of cylinder equals to A and displacement of the piston is dx. So the increased volume of the gas A dx equals to dV, because we know volume is the product of area and displacement. Now work done for very small change in volume dV at constant pressure, dW equals to pdV. This is equation number 1. Dear students, you can also see a diagram which is PV graph for isothermal expansion. Here x-axis is volume and y-axis is pressure, and 2 points which is initial volume V1 and final volume V2, and the expansion of volume of the gas is dV. You can see in the figure. Now the total work done to increase the volume of the gas from V1 to V2, W equal integration V1 to V2 pdV, equation number 2. We know for 1 mole of ideal gas, PV equals to RT or P equals to RT divided V. This is equation number 3. Now from equation number 2 and 3 we get W equals to V1 integration V1 to V2 into RT divided V into dV. Since here V is the variable and RT is the constant, so we can write W equals to RT integration V1 to Vt integration dV by V, and you know the rules of integration dx divided x equals to ln x. Ln x means a natural logarithm whose base is a. So we can write integration dv by v equals to ln of v. Now the expression becomes W equals to RT, third bracket ln V, third bracket V2, V1 to V2. Here V1 is the lower limit and V2 is the upper limit. Or W equals to RT into ln of V2 minus ln of V1. Therefore, W equals to RT ln of V2 divided V1. This equation is the required equation for 1 mole of ideal gas. But if the number of moles of the gas is N, the equation becomes W equals to nRT ln V2 divided V1. The students, you know, number of moles N equals to small m divided capital M. Here small m is the mass of the gas and capital M is the molecular mass of the gas into RT ln of V2 divided V1. This is the required expression for n mole gas or n mole of ideal gas. Now we discuss another work done for ideal gas in adiabatic expansion process. Okay, here is two figures you can see. In figure 1, a cylinder, a gas, 1 mole of ideal gas is kept with a frictionless piston of temperature T, volume V, internal energy U, and pressure is P. Since the process is adiabatic process, so here no heat enters the system or cylinder, or no heat released from the system or cylinder. Let area of the cylinder is A and displacement of the piston is dx, so increase of volume equals to A dx equals to dV. Now, work done for very small change in volume dV at constant pressure dW equals to P dV. This is equation number 2. Now, dear students, you can also see a graph of TV for adiabatic expansion. Here, along x-axis is temperature and y-axis is volume, and the change of volume from V1 to V2 and increased volume equals to dV. Now, the total work done to increase the volume from V1 to V2, W equals to integration V1 to V2 P dV. This is equation number 2. The students, we know for adiabatic process PV gamma equals to constant, here constant equals to K, or P equals to K into V to the power minus gamma. This is equation number 3. Now from equation number 2 and equation number 3, we can write W equals to integration V1 to V2 into K V to the power gamma minus gamma into dV. Since here K is the constant, so we can write W equals to K into integration V1 to V2 V to the power minus gamma into dV. Now, according to the law of integration, we can write the equation W equals to K into third bracket V to the power minus gamma plus 1 divided minus gamma plus 1 third bracket close from V1 to V2. Or W equals to 1 by 1 minus gamma. Here 1 by 1 minus gamma is common. We can write K V2 1 minus gamma minus K V1 1 minus gamma. This is equation number 4. Again, we know for adiabatic process P1 V1 gamma equals to P2 V2 gamma equals to K. Therefore, W equals to 1 by 1 minus gamma the value of K is placed P2 V2 gamma into V2 1 minus gamma minus P1 V1 gamma dot V1 1 minus gamma, or W equals to 1 by 1 minus gamma into P2 V2 1 minus gamma plus gamma minus P1 V1 1 minus gamma plus gamma. Here plus gamma and minus gamma is cancelled. Also here minus gamma and plus gamma is cancelled. So we can write W equals to 1 by 1 minus gamma P2 V2 minus P1 V1. Or W equals to 1 by 1 minus gamma RT2 minus RT1, since according to the law PV is equal to RT, we can write this equation. Now common R, W equals to R divided 1 minus gamma T2 minus T1. This is the equation required expression for 1 mole of ideal gas. But n moles of ideal gas, the equation becomes W equals to NR divided 1 minus gamma T2 minus T1. Dear students, now from the two expression we can get three expression. W equals to nRT ln V2 by V1 equals to small m by capital M RT ln V2 by V1. This expression is applicable for isothermal process. Number 2, W equals to 1 by 1 minus gamma P2 V2 minus P1 V1. This equation for adiabatic process. Also number equation 3, W equals to ANR divided 1 minus gamma T2 minus T1. This equation is also applicable for adiabatic process. Dear students, here you can see three equation which are for isothermal or adiabatic expansion. But for contraction, these three equation becomes, for contraction, the three equation becomes W equals to minus nRT ln V2 divided V1. Number 2, W equals to minus 1 by 1 minus gamma P1 V1 minus P2 V2. And number 3, W equals to NR divided 1 minus gamma T1 minus T2. Dear students, now we will solve some mathematical problem regarding this formula. Now mathematical problem number 1. .02 kg hydrogen gas was compressed to 1/4 of its volume in isothermal process at 27 degree Celsius temperature. Find out the work done. Now, the information in the question is mass of hydrogen gas, atomic mass M equals to 0.02 kg, and molecular mass of hydrogen gas, you know, capital M is equal to 2 gram. That means we can write 2 into 10 to the power minus 3 kg. Let initial volume V1 equals to V, therefore final volume V2 equals to V by 4. And temperature T equals to 27 degrees Celsius. Now convert to Kelvin. 27 plus 273 Kelvin equals to 300 Kelvin. Work done, W equals to what? We know W equals to small m divided capital M RT ln V2 by V1, or W equals to the value of small m equals to 0.02 kg, capital M equals to 2 into 10 to the power minus 3 into value of R Here R is the universal gas constant whose value is 8.314 joule per mole per Kelvin into temperature is 300 Kelvin into ln. Here the value of V2 equals to V by 4. So we can write V ln V by 4 divided the value of V1 equals to V. Therefore V. After calculation, the work done W will be minus 34576.95 joule. Now, mathematical problem number 2. In a cylinder, there is 1 mole diatomic gas at 300 Kelvin temperature. The gas is expanded adiabatically. The ratio of expansion is 1:2. Calculate the work done for the expansion. Here, dear students, the value of number of moles is 1. Ratio of the volume expansion V1 ratio V2 equals to 1:2. Initial temperature T1 equals to 300 Kelvin. Since the gas is a diatomic gas, students, you know the value of gamma for diatomic gas is 1.4 and work done W is equal to what? Since here T2 is not present, so first we find the value of the temperature T2. You know T1 V1 gamma minus 1 equals to T2 V2 gamma minus 1, or T2 equals to T1 V1 gamma minus 1 divided V2 gamma minus 1. Or T2 equals to T1 into whole power of V1 by V2 gamma minus 1. Now putting these values, T1 equals to 300 Kelvin and V1 equals V1 and V2 ratio 1/2 whole power 1.4 minus 1. Now after calculation, the value of the temperature T2 will be 227.36 Kelvin. Again we know W equals to NR divided 1 minus gamma T2 minus T1, or W equals to the value of N equals to 1 and R 8.314 divided 1 minus 1.4, since the value of gamma equals to 1.4 and value of T2 equals to 227.36 and value of T1 equals to 300. Therefore, after calculation, the work done W will be 1525.44 joule. This is the required answer. Dear students, now we will solve some creative questions related these formulas. Now, creative question number 1, that means CQ1. You can say STEM 2 students, Susan and Shomon of class 12, compressed a volume into half of 1 mole of a diatomic gas at 27 degrees Celsius temperature and 300 centimeter mercuric pressure in isothermal and adiabatic process respectively. Question number C. What is the temperature of the gas according to the thermodynamics cells created by Schumann? What is the temperature of the gas according to the thermodynamic cells created by Schumann? So, we will find the temperature for Schumann. The process of Schumann is, you can follow the process is first, second man Schumann, the process is adiabatic process. Now, let initial volume V1 equals to V, therefore final volume V2 equals to V divided 2, since the volume will be half. Initial temperature T1 equals to 27 degrees Celsius equals to 300 Kelvin and final temperature T2 equals to what? Since this is a adiabatic process and the gas is a diatomic gas, so you know the value of gamma equals to 1.4. Now we can write the equation T1 V1 gamma minus 1 equals to T2 V2 gamma minus 1. Or T2 equals to T1 V1 gamma minus 1 divided V2 gamma minus 1, or T2 equals to T1 into V1 by V2 whole power gamma minus 1. Now putting these values, value of T1 equals to 300 Kelvin and the value of V1 equals to V and V2 equals to V by 2 whole power 1.4 minus 1. Therefore, after calculation, the temperature T2 will be 395.85 Kelvin. This is the answer of equation question number C. Now we will discuss question number D. First, in case of Schumann, since the process of Schumann is adiabatic process, so we can write the work done W1 equals to NR divided 1 minus gamma into T2 minus T1. And value of N equals to 1 and R equals to 8.314 divided 1 minus 1.4 into value of T2 equals to 395.85 minus 300. Therefore, W1 equals to minus 1992.24 Joule. Now, in case of Suzanne, W2 equals to nRT ln V2 divided V1. Since you can see the process of Suzanne is an isothermal process, so we can write the equation W2 equals to nRT ln V2 divided V1, or W2 equals to value of N equals to 1, R equals to 8.314 and temperature T equals to 300 into ln V by 2 divided V. So, W2 equals to minus 1728.85 joules. Dear students, here you can see since W1 is greater than W2, therefore after mathematical calculation we can see that Schumann will do more work than Suzanne. Now, CQ number 2, you can see another creative question in the board. 2 gram helium gas is stored in A and B cylinder. Cylinder is A and here cylinder is B, with a frictionless piston at 27 degree Celsius temperature and 2 atmospheric pressure. Cylinder A is made by conductive and cylinder B is made by non-conductive material. Both pistons release force F. Dear students, you know for conductive materials the process will be isothermal process, and for non-conductive material the process will be adiabatic process. So, question number say find the temperature of the gas in cylinder B. You can see here B is non-conductive materials. So, here this process will be the adiabatic process. Now, we can solve question number C. Here, mass of gas is small m equals to 2 gram, and the gas is since helium, so the molecular mass capital M equals to 4 gram. Initial pressure P1 equals to 2 atm. 2 atm means 2 atmospheric pressure. Therefore, final pressure P2 will be 1 atm. since the piston is released, so the initial final pressure will be 1 atmosphere and initial temperature T1 equals to 27 degrees Celsius equals to 300 Kelvin. Final temperature T2 equals to what? And since the gas is monoatomic gas, so the value of gamma 1.67. We know T1 P1 1 minus gamma divided gamma equals to T2 P2 1 minus gamma divided gamma, or T2 equals to T1 into P1 by P2 whole power 1 minus gamma divided gamma equals to the value of T1 Now putting the value T1 equals to 300 into P1 2 divided P2 1 whole power 1 minus 1.67 divided 1.67. Therefore, T2 equals to 227 Kelvin. This is the required answer of equation number C. Now, dear students, we can solve the equation number D in the previous system. Now, for cylinder A, work done. The formula will be, since cylinder A is a process of isothermal process, so the equation will be nRT ln V2 equals V1 equals to nRT ln P2 by P1. For cylinder B, the equation will be nR 1 minus gamma divided 1 minus gamma into T2 minus T1. If you put the values, these two equations, then you will get the required result. And you will also see the result W1 will be greater than W2. Dear students, you can solve regarding this STEM in home. Thank you to all. Stay safe, stay well. Allah Hafiz.